Hello friends, welcome to VK lectures. In this lecture, we will be discussing the question number 64 from Kannada Set 2024 physics question paper. Now, which of the following statement about Bose-Einstein condensation of a gas is false? Now, here we are going to use the elimination method. To check the correct answer. Elimination method along with contradicting statements. Contradicting statements means statements which give two opposite meaning. So this is what we are going to search. Now the question is, which among the following is false? So among the four statements, three statements are correct. And one is false. One of the statement is false. Now let us read each option one by one. The pressure in BE condensed gas depends on the temperature only. The pressure in BE condensed gas depends on number of particles. Pressure in BE condensed gas is independent of number of particles. The finite number of particles in the condensed gas have zero momentum state. Now you see, look at the option 2 and 3. Option 2 and option 3. Pressure in a BE condensed gas depends on number of particles, and the third statement is pressure in BE condensed gas independent. So these two are the contradicting statements. If this is true, this will be false, and if this is false, this will be true. So our answer is either 2 or 3. If our answer is either 2 or 3, then both of the statements 1 and 4 will be obviously correct, because the wrong answer is either 2 or 3. Now we take that 1 is correct, because our answer is only either from 2 or 3. If 1 is correct, that means the pressure in BE condensed gas depends on temperature only. That means the pressure do not depend on any other parameter. Pressure depends on P of T only. No other parameters exist. That means it does not depend on anything. So P is equal to P of T, and if I write P is equal to P of N, this is a wrong statement. That means it does not depend on number of particles. So check 2 and 3. Pressure in BE condensed gas depends on number of particles. So this will be a wrong statement. And the third statement, you look at pressure in BE condensed gas is independent of number of particles. So independent. It does not depend on number of particles. So this is a true statement. So among these, 3 will be the second option is a wrong answer. So it's our the statement which is false. So this is how we can find the answer from contradicting statements in the options. By using elimination method, we have found the answer without applying any physics. Though we have found the answer without solving directly or without using any physics, just by analyzing the options, it is important to understand the physics behind this Bose-Einstein condensation, and also all the options one by one. So let's move on to the first option. Now let us see the statement one by one. Statement 1. Pressure in B condensed gas depends on the temperature only. Now, uh, what is B condensed gas? This is Bose-Einstein condensation. So, BE condensed gas has some properties. That is, this condensation will occur only below the critical temperature. Critical temperature Tc. So the condensation will occur only below Tc, and in at Tc the chemical potential will tend to 0. Mu will be tending to 0 at this point. Okay. Now the grand potential means the grand canonical potential. Given by Ohm is equal to minus Kb, Boltzmann constant Kb, times T into sum over I log of e to the power 1 minus e to the power minus beta times ei minus mu. Okay, so this is the grand canonical potential, and its potential has a unit similar to the energy. Okay, now once we got this, we have the pressure. Now we need the pressure. Pressure is given by P is equal to minus omega by V. So omega has a unit of energy, so PV. So it's like just like PV equal to nRT, something we write, right? Yeah. So similar to that, we have this unit. So pressure is equal to minus omega by V. Now we can see that the pressure depends on the temperature only. So if you remove this uh, condensation, that means the first statement, if you look at the pressure in a B condensed gas, so pressure, so this is proportional to what? T only. So this is, so pressure in condensed gas depends on temperature. Now let's see what is Bose-Einstein condensation. Now for any normal matter, the particles will move randomly. But some particles such as bosons, let's say bosons. Now bosons have integral spin. Spin 0, spin 1, etc. Okay. Now what is the property they have apart from the normal material or normal particle? These bosons have a special property that they can share the same energy state. Share the same energy state. This is one property of bosons. Share the same energy state means any number of particle. This is also very important. Any number of particle can share the same energy state. Okay, or same quantum state you can write. Same quantum state can be uh, occupied by bosons, n number of particles. So at certain temperature, at a temperature, let's say below the critical temperature Tc, at temperature less than Tc, less than the critical temperature Tc, this sharing occurs, sharing of same state occurs. So this will allow for condensation. Condensation means what? Grouping together. Group together. Now earlier we had, that means above the critical temperature, uh, some Ni particle was in psi I state, then N1 psi 1, N2 in psi 2 state, and N3 particle in psi 3 states. Now when you go below Tc, the critical temperature, everyone will occupy the lowest energy state. So lowest energy state, all the particle is going to occupy the lowest energy state. The what is available is psi 1 here. Okay, so when everyone goes to this, all the particle come together. So from the micro state it moves to macro state. Okay. That means here we have individual particles, and in the case of macro state you have group of particles occupying the same energy state. Here few particles occupied the first state, few particles the second, few particle the third, likewise. But in this case all the particle is occupying the same ground state. This is called the Bose-Einstein condensation. They pile up to form the large fraction. Okay, so this situation, as we say, it is called Bose-Einstein condensation, and this will not occur. Uh, so some conditions are there. As we mentioned, it has to be integral spin. Integral spin. So this you cannot expect in fermions, such as protons or electrons. Now integral spin, which all go for this, examples are photons, bosons, helium 4 atom is example. Now here we have the statement 2. The pressure in a BE condensed gas depends on number of particles of the gas. Now let's see what is number of particles. Number of particles is the N0, that means N0. This is the condensate fraction. Condensate fraction. That means the fraction of the particle, number of particles that is present in the condensed state. Okay. Now sorry, we can write n equal to n naught and n excited. So this is excited particle, excited number of particles. So or it's also called excited fraction, excited particle or fraction. So these are the two kinds of particles. So total number of particles will be equal to n naught plus n excited. Now n naught, which is in the condensed state, this will not contribute to pressure because it is not moving, do not contribute to pressure. Why? Because this is at the lowest energy state. Lowest energy state means where energy is zero, energy state. So this energy is nearly equal to zero for this particle. So energy is zero means there is no motion. So kinetic energy equal to zero, which means velocity is zero. When there is no velocity, what is pressure? Pressure is defined as how much it hits the container, walls of the container. If this is the container, particle has to hit the walls, only then pressure will be generated. So in the lowest energy state, where kinetic energy is zero, where velocity is zero, there is no pressure. Okay, now this one, only excited particle will contribute. That means n excited contribute to pressure, because excited particle means the particle is present in excited state. Particle present in higher energy state. Higher energy state means obviously E is not equal to 0, which means they have either kinetic energy or the potential energy, which means they will hit the walls of the container and generate pressure. But below T less than Tc, n excited is equal to 0, which means total number of particle is equal to n naught. There will be no particle present in the excited state, n naught. So which means pressure in a B condensed state is independent. P is not equal to P of n. It is only excited particle which contributes. So since now there is no excited particles there, it is independent of the number of particles. The statement 3, pressure in B condensed gas is independent of number of particles. So this is what we have just shown. It depends only on the temperature and do not depend on number of particles. But let us see some more points regarding this. So pressure P is equal to 2 by 3 times U by V, where U is the energy, V is the volume. So what is U? U is equal to sum over I EI divided by e to the power beta EI minus 1. Energy of the particle or the energy of the state. Now here we can see that pressure is equal to P of the energy U and P of V. It is inversely proportional to V. Now adding more particles just increases A naught. Now if you want to add more particles, so let's say there is a state, already some energy particles are there. It's a single energy state EI. Now if I am adding more particles are being added. Now where it will go? It will go to the same energy state. The higher energy state is still vacant, if provided the temperature is less than Tc. Unless the temperature is less than Tc, you can keep adding the particles. It will go to EI or E1 and not E2. Okay, so all these particles contribute to N naught, and only when it goes to here it is called N excited. So as long as the particles are in EI state, the particle is N naught and it do not contribute to any pressure. Statement 4. Finite number of particles in the condensed gas have zero momentum state. Now what is this telling you? Now we know that the condensed state, there is a condition that T should be less than Tc, the critical temperature Tc. So macroscopic number of bosons fill the lowest energy state. So macroscopic number of bosons will accumulate or condense to the lowest energy state. Now the lowest energy state, the momentum is 0. Why momentum is 0? Because velocity is 0. Momentum is P is equal to mv. If v is 0, momentum is 0. So it goes to the zero momentum state. That is why it is called the lowest energy state. Okay. Now yes, so now we say it's a momentum state is 0, and now let's see what is the fraction in the condensate. Now the fraction in the condensate means the state, N naught, how many particles are in N naught divided by the total number of particles. This is at any temperature T. So at a particular temperature T, the condensate is given by N naught by N equal to 1 minus T divided by Tc to the power 3 by 2. So this is how it goes. When T equal to Tc, N naught by N will tend to 0. What does that mean? Now from the lowest state, lowest temperature, below Tc, all the particles are in ground state or lowest energy state. Now as and when we increase the temperature, as temperature increases to Tc, that means when temperature tending to Tc, then there is no particles will be present. present in ground state or lowest energy state. So this is equation is applied below TC.